So today, to finish up talking about sorting, we have a few topics. Quicksort is one. Bucket and Radix Sort is the other. What's so funny?
How did they know they could call it Quicksort when they made it?
It's like I was born in 4 BC. It's like Christ was born 4 BC, right? It's like a coin minted 4 BC. That's what it's like. Yes, you know, I don't know the history of when Quicksort was called Quicksort, but it is an interesting sort. The interesting thing about Quicksort is that if you analyze its worst case, it's not so quick. Its worst case is order n squared. Oh, a brief 20-second note. You might notice that throughout this course, I don't always write a big theta. Sometimes I just write a big O. And almost every time I write a big O, it should be a big theta. It's just that the notation big theta didn't become standard until after I was long used to just writing big O. Big theta just means that whatever the polynomial complexity is, that it's bounded above and below by n squared. And usually big O kind of implied that, but it doesn't anymore. And when I write big O, I usually mean big theta. So you thought so. All right, so the worst case of Quicksort is order n squared, but really it runs very fast because of the name. Anything you name quick runs quickly. And the average case is n log n. And we're going to follow our strategy of keeping the big picture, talking about techniques and applications, and staying away from the details of the math, but still showing you where the math fits in. This is going to be easy to explain mathematically, and this is not going to be easy to explain mathematically, but I'll show you up to the point where it gets hairy. All right. Bucket and Radix sort are generalizations of a really simple idea called counting sort, or what the book calls counting sort. And they are attempts to make sorting linear time. Now I'm going to convince you today, before we quit, that if you do any kind of algorithm that uses comparisons, whose major tool is compare this element to this element, and if one is bigger, do this, and if the other is bigger, do this. If that's your main tool, then you can never do better than n log n. All these methods don't use that tool, and they manage to get order n, but it's kind of a pseudo-linear time. They both, in their own way, are assuming a particular restriction on the input data. And if that restriction is not there, then neither one of these run in linear time. So the lower bound of n log n that we know of for sorting is, for all intents and purposes, really there. And you can't do better than n log n. All right, I'll do that lower bound later. And I should mention that in general, lower bounds are hard to prove. It's easy to prove upper bounds on problems because you just come up with an algorithm that works, and that gives you an upper bound. You come up with a better one, that gives you a better upper bound, and you keep moving your way down just by getting one algorithm that works. But if you want to show a lower bound, you have to show that no matter what algorithm you try, they're all going to take more than that amount of time. And that's a real tall order because you have to make an argument that works for every algorithm in the whole world. That's what makes things like proving problems are really hard. It makes that difficult. That's why we have NP-complete. NP-complete doesn't mean the problem's really, really hard. It just means it's probably really hard. And I'll tell you what that means in detail a little later. But lower bounds are much, much more difficult than upper bounds as far as algorithms go. All right, so that's our big picture. The lower bound for sorting, Quicksort, Bucket, and Radix sort, and what the special restrictions that the underlying assumptions are making there. OK, questions about this? Right, so let's start with Quicksort. Quicksort is actually really relatively easy to understand. It's not a fancy sort. It just happens to work well. And a good way to think of it is that it's kind of it's related mildly to merge sort, very mildly. Merge sort splits the array into two halves, recursively sorts each half, and then merges them. All right, so it does recursion first, and then it does gluing. Quicksort does the same kind of splitting, but first it does the work, and then it does the recursion. So here's what Quicksort does. Quicksort takes the array, figures out a way to, it's called partition, that's the word that's always used with Quicksort, to partition it into two parts, where one part is smaller than the element that it's chosen to partition on, and the other part is bigger than the element that it's chosen to partition on. It typically chooses to partition, the easy way to do it is partition on the first element. So when it's done partitioning, 37 will be somewhere in the middle, and all the things bigger than 37 will be to the right, and all the things smaller than 37 will be to the left. That's going to take some work. That's called the partition procedure. Once the partition procedure is done, how do you proceed? What do you do then? You got everything bigger than 37 here, everything less than 37 here. You recursively call Quicksort on the first part. That gets sorted for you magically. You recursively call it on the second part. That gets sorted for you magically. And since all the parts less than 37 came first and all the parts bigger than 37 came second, if each of those are sorted, then the whole thing's sorted. Okay, so you do the gluing first in some ways. Or instead of gluing the two subproblems together, you do a preparation. And then you send your recursion subproblems out. Okay, who gets it so far?
Together because it's an in-place sort. There's no gluing involved.
Right. There's no gluing involved. There's just preparing before you send them out. Right. And it is an in-place sort. We're going to just keep using this array. Ideally, yes. Good. Other comments, questions? All right. Before I show you how to do partition, which is the only part of Quicksort that actually needs any description, let's analyze how long it takes in the worst case. What's the worst thing that can happen when you partition your array into two parts? Well, the best thing that can happen is that it splits right down the middle. That's the same as merge sort. Merge sort, you actually always split down the middle. You never have a lopsided split. But here, you're getting lucky if you get an even split. If 37 happens to be the middle element, then you're going to get a half and half split. And then your recursion ends up being two parts of size n over 2. And you get the same, this is the best possibility for Quicksort. You get this recurrence equation. T of n is 2 times T of n over 2 plus whatever time it takes to do the partition. Okay? It's this part which is the best possible. What's the worst possible? The worst possible is that they're completely unbalanced. That you get T of 1 and T of n minus 1. Now let's say for a moment, since merging took linear time, that gluing step, let's hope that the preparation step, the partitioning, also takes linear time. So that over here we have n and over here we have n. You should know from merge sort that this ends up being what? N log n. And you can check it. And God knows you probably did a nice recitation on this, and hopefully you're feeling more comfortable with this. This ends up being n log n. That's the best we can hope for Quicksort. What does this end up being? Well, this is a constant T of 1. So that doesn't really matter. I mean, that's bundled up in the n. N is more than a constant. So this is really the same as Tn equal Tn minus 1 plus n. What's that recurrence get you? Gets you triangle numbers, right? Tn is Tn minus 1 plus n. Tn minus 1 is Tn minus 2 plus n minus 1. And when you do the substitution, what you end up getting here is n plus n minus 1 plus n minus 2 plus n minus 3 all the way down to plus 3 plus 2 plus 1. You get triangle numbers. And triangle numbers are order n squared. Do you see why I tortured you so much 2 months ago? You just need to know this stuff. It just comes up all the time. It's got to just feel like, oh, I don't have to think about it. Yeah, I know triangle numbers are order n squared. Yeah, right. You got to feel like it's your ABCs. No, I just like to torture you. All right, this is the best you can hope for. This is the worst that's going to happen. Now, if we just pick the first element to do the partition on, there's no reason to assume that we can avoid this worst case. It's going to happen. Now notice this recursion happens a lot. Once you split it up, you get another recursion. So the chance of it happening every single time is really slim. I mean, sometimes it's going to be somewhere in the middle. Sometimes it's going to be more lopsided. And we might wonder what happens on the average. And we'll deal with that in a minute. But that's where we are right now. So are there questions so far? Yeah, Donna.
Just going back, what do you do with the middle point? Which side do you stick it on? Do you just choose?
The 37?
Yeah.
It's going to end up right where it belongs, in the center
But
somewhere.
then when you split to resort each half, which side does it go?
Oh, take your pick.
Okay.
Yeah. I don't know. I don't know what it actually is in the book, is what I'm saying. It's the left one?
It's the end of the
So it's the left
You
one.
wouldn't want it to be the first of your other element,
Right,
because then because that would be unbalanced and you would never.
You can
Then
get
you
an
have an
infinite
element of
loop if
one,
you pick.
yeah.
Okay, but let's go here and figure out how we can calculate some kind of an average case recurrence equation. Now, you never really want to do an average case by looking at all possible n factorial inputs and then dividing over them, because it's just ludicrous. You want to be able to put your different inputs into categories, like we did at least briefly for insertion sort. So let's do it here. Let's assume that we're equally likely to have the first element end up partitioning, 1 and n minus 1, 2 and n minus 2, 3 and n minus 3, halfway, and then n minus 1 and 1, n minus 2 and 2. Let's assume that it could be partitioned equally in any one of the spots. You know what I mean by that? So the 37 is going to end up someplace here. Let's assume that it'll end up equally likely in any one of the spots from the first all the way up to the last. Okay so far? So let's write an average case recurrence equation. It isn't so tough to write it, it's just hard to solve it. Here's the average case for Quicksort. Well, how many cases do we have? We're going to divide up all the possible cases into n possibilities, where the partitioned element can end up in any one of these spots. And let's write the recurrence equation we get for each one and divide by n, and that'll be the average case. So what do we get? We get t of 1 and t of n minus 1 plus t2, tn minus 2. And we keep going all the way down to t of n minus 1 and t of 1. And we divide this all by
N minus 1.
And
You have to put a factor of 2 on the first. T1 plus Tn minus 1 occurs twice. You have n different numbers, and you're going to get n minus 1 different sums here. You have to, for whatever reasons, because of the definition, the first of those statements occurs twice.
okay, so let's see exactly why. If it ends up being in the first spot, we get it split up 1 and n minus 1. And if it ends up being in the last spot, we get it split n minus 1 and 1.
But if it ends up being in the second spot, we also get 1 and n minus 1 because it's the...
What if it ends up being in the second spot? Not the second spot. That's 2 and n minus 2. What if it ends up being in the second to last spot?
So that's twice.
If it's the second to last spot and we include it at the end of the left side, that's also the same as n minus 1 and 1. So if our 37 ends up here or here, we still get the same two cases at the end. This is a real detail that actually won't have any effect on the final solution, but it's a detail you should check. All right, so we get this big, big, big equation.
In the equation above, you had an n at the end. For the
We're going to have to put n on each of these, right? So it's right?
Is there a division here?
Yeah. All this gets divided by n, by the number of different classes of cases that we have. That's the recurrence equation. So go solve that by substitution. This is a mess. This is quite challenging. And if we hadn't spent so much time doing discrete math, then I might have taken the next 45 minutes to go ahead and actually solve this explicitly. The way the book actually handles it, and I think it's the way most texts handle it, is that what are you hoping for here? You're hoping for n log n, right? So why don't we just guess that the solution's n log n and use this and prove it by induction. We did that technique a couple times in discrete math. Guess your answer and prove it by induction that it's right. Recurrence equations are a super way to use inductive proofs because you can assume that the closed form can be substituted into here because these are smaller cases than the T of n. So going through the details of that turns out not to be so bad. I'm not doing it. This is where I'm stopping. I want you to realize that this is a big summation of recurrence equations. The best technique is guessing the answer, proving it by induction, or I should say the easiest technique. But there are explicit techniques to solving this directly and in closed form. And whichever way you choose, you will get n log n when you run through this. Okay, and I'll leave this possibly for an advanced recitation or looking at it on your own when and if you have interest to do it. But a mathematician could help you, and so can I, work your way through it. But you should know the result, and don't worry so much about the details right now. Questions about it so far?
Are there all kinds of fine-tuning to get that partition element? That when you partition?
Yeah, there's probably a dozen papers that talk about good ways of choosing the partition element. Absolutely. Because clearly that's the sore point in the algorithm. But you don't want to spend too much time getting a good one, because just by doing it randomly, the average case doesn't turn out so bad.
But is choosing the first element all that random?
Well, I mean, we're assuming it's random in the sense that we're assuming it's random where it's going to end up when we're done partitioning. So I guess the point is randomness here isn't so bad.
No. Randomness is good. In fact, randomness is the best thing, right? Because you're dealing with...
Well, now the best thing would be if the first number always ended up being the median. Then we'd know we get a half and half split.
Yeah, but we're doing a sort, so we don't know that.
We don't know that. Right.
I'm just saying that sets of numbers are never completely arbitrary except in an academic context. So you know something about it.
There's probably, right. You might be able to leverage some pattern. Yeah.
How about I pick the middle one? If you're going to pick one.
Pick the middle one.
Just, you know,
Look what happens here when we pick the middle one. It's not so hot. But OK, well,
maybe it's like partially loaded.
you know what I think actually is one common way to do it is you take the first and the last and the middle, and you take the middle of those. I think that's one way. Another way is to calculate. There's a lot of different ways. Look.
Make a random number generator.
You can do that too. Just pick one at random. Well, let's figure out how to do partition first, because it isn't so bad, and there's a lot of different ways to actually implement this. Your book has an exercise that discusses an alternative to the one that's done in the text, and the one I'm going to describe is, I'm pretty sure, the same one that they talk about in the text. It's the kind of standard one, and it's very straightforward. Here's how it works. Start. I'm going to call them pointers because I'm making arrows, but they're really simply indices to this array. Start your two indices at the second spot in the array and at the last spot in the array. And here's what we're going to do. We're going to move them toward each other until they go crash. When they go crash, we're going to have all the heavy ones bigger than 37 on the right side, and all the light ones lighter than 37 or equal to 37 on the left side. So we're going to move them in. As we move them in, we want to make sure that what I said is true, that the things to the right of that right arrow are bigger than 37, and the things to the left of this left arrow are smaller than 37. So here's what I do. I just take the arrow, and anytime I get something that's bigger than 37 on this side, I just move the arrow down, and anytime I get something that's smaller than 37 on this side, did I say that right?
The other way around.
If I have something bigger here, I have to stop, and if I have something smaller here, I have to stop. So right now I have to stop.
Don't you start with 37 rather than 45?
No, you leave 37 here. That's going to be put in at the end in the middle. You'll see. We're just going to have this sitting here, and we're going to move our arrows together. So 5 and 45 are on the wrong sides. So we swap them. And now we move the pointers in one each.
And if only one of them was on the wrong side, we would have moved the other pointer until we found it.
You move the pointer.
You move the pointer until you get something on this side that's bigger than 37, and you move the pointer here until you get something that's smaller than 37. So in this case, we didn't have to move it much at all.
Until the other pointer stops moving before.
Right.
Doing it.
Right. Exactly. Right, Doug. So in this case, we're already there. This is already in the wrong spot, but this is okay, and this is okay, and this is okay. So this guy moves all the way down to here, and now we're ready to do another swap. So this becomes 36, this becomes 52, and now our pointers crash. They cross each other. See how I had them at an angle? You see they cross each other when you do that. So you just tell the computer, angle them, and watch when they cross. You can tell when they cross because, well,
You know what the number is.
you know what the number is, right. So you can, there's just a little while loop that tells you when to stop. Sometimes they cross and sometimes they end up at the same spot. There's some details here that I'll leave for you to look at when you look at the code. It isn't automatically going to be perfect. You could get a bug if you're a little careless. But now what do? There's one more step. You make sure you take this one, which is the rightmost of the left side, and you swap it with your partition. So this is the last step. The 36 comes here, and the 37 goes here. This is the pivot point, and you can see in this example, we end up with 1, 2, 3, 4, 5, 6 on the left, and 2 on the right. Somewhere not particularly balanced, but not the worst case either. Are there questions about this process?
I don't understand why you're swapping the 36 with the 37.
Because our whole goal was to get this thing partitioned into 2 parts, where 37 was the split spot.
Okay.
So we got to make sure that that's in the middle. So at the very last stage, we basically say, hey, where was that crashing point? Make sure 37 gets swapped with the right end of the crashing point.
Okay.
Does that make sense, Andrew?
Yeah.
Okay. How long does it take? Well, basically, you're moving these pointers in one step at a time. You don't do anything except move them in. Every once in a while, you stop and you do a swap. And then you continue to move them in. Each of these pointers moves in 1 at every step. So it takes order n. There's nothing tricky about it. The worst case is you have to do a swap every time, in which case it's 2n. Or if a swap takes 3 steps, 3n or 4n. But it's proportional to n. There's nothing crazy that goes on here. Nothing squared, nothing cubed, nothing borrowed, nothing bloobed, nothing. It's fast. Yes. This is Quicksort. Are there questions so far? It's called Quicksort. Heap sort is in place. Heap sort's in place. Merge sort's not in place. Heap sort is in place. This sort, look, it just happens to be when you do tests. This is about as faster than all the other. It doesn't take any extra space. Well, kind of. There's recursion involved here, so there's a stack that could be log n deep. But it doesn't take order n extra space. I think, if I remember right, I once read a study that said if you really want to sort as fast as possible, the best thing to do is use Quicksort until the lists get down to size 10 or less. Then stop using Quicksort and use insertion sort. So a hybrid like that might actually be the fastest, where you recurse down, check if the length of the list is 10 or less, then throw it to insertion sort, which has no overhead on the recursion and which runs very, very quickly, especially if those 10 are almost sorted, which they...
10 or less is not very many, right?
Yeah, so...
Geez, before you know it, it's going to be over, right?
Yeah, maybe. I don't know. I mean, I once gave an assignment where I had people just experiment with all sorts of hybrid things and timing it, and I don't know. It's fun for the first half an hour, and then it starts getting boring. It's like, it depends. these kind of engineering experiments can be really fun until the results stop being consistent. You know, until sometimes this is the fastest and sometimes the other one, and then you have no idea why, and then you say, ah.
What is the implementation of this iteratively like? Does it get really, really bad?
Yeah, I mean, I don't know any way to do this iteratively except to explicitly store the stack of where we're up to. Except to explicitly simulate the recursion, I don't know any way to run this without recursion.
Because a billion numbers could really...
Well, it's still the log of a billion is not so much. It's just 20. So you only have a stack that's 20 deep. It's not so bad. The worst case would be bad. In the worst case, you'd have a stack that's a billion deep. But when you average it out, it turns out that doesn't happen. Sometimes averaging helps. Averaging usually doesn't help. It happens to help here. That's why we do it. One good thing to take away from Quicksort, which I think is really worthwhile, is when you think of an algorithm and you're thinking about using recursion as a technique, think about you get the subproblems for free. You can get them for free at the beginning, or you can get them for free at the end. You can prepare your data and then get the subproblems done for free, or you can get the subproblems done for free and ask yourself, what am I going to do now that they're back and they're all done? So in merge sort, you ask yourself, well, what do I do with two half-sorted lists? I can merge them in linear time. You've got a sorting algorithm. Another way to look at it is, what do I do if I want to just give two parts of my list to people and say sort them, and when they come back it's all done? Then you better give them two parts, one of which is a smaller than all the elements in the other. So that motivates partition. If you think about doing your gluing or preparing before or after so that you get your free recursion then, it gives you a little angle in which to leverage your algorithm thinking. And you should do that all the time with any algorithm.
What do you mean the subproblems are free?
I mean that you don't have to worry about how they're going to get done. You're actually going to construct the algorithm by concentrating on how to connect the subproblems rather than by worrying about the step-by-step. I don't mean they're free computationally. All right, other questions? Good. Let's shift gears for a second and talk about lower bounds. I mentioned before there's an n log n lower bound for sorting. That means you're never going to do any better than that. That's the best you can ever hope to do. And a way to prove that requires that whatever method anybody comes up with, you are going to have to argue about that method. So whatever argument I come up with on the board here has to be an argument which works with any method anybody could come up with. And the way we are going to do this is with a technique that can be used in other situations. So it's worth understanding this technique in general, but it doesn't have universal applicability. Sometimes you don't get very good lower bounds with this technique, but it's still a neat technique. And the idea is this. Let's assume that what we're really measuring is comparisons. So any algorithm that uses comparisons, I will be able to make this argument about. If your algorithm doesn't measure comparisons, then this will break down. But assuming your algorithm is measuring comparisons and using comparisons, then I will convert any algorithm you come up with to something called a decision tree. You write a program, and I will stare at your program and come up with a tree that represents your program. And a decision tree is not a fancy thing. It's pretty logical. Here's what the tree does. Anytime your program has an if statement that compares one element in the array to another element in the array, I put a node in my tree. And I'll put the two indices of the nodes that you're comparing. Say index 7 versus index 8. Let's say that's the first thing you look at. Maybe we should be more practical. Well, say your algorithm was bubble sort. What would be the first two things you look at? It would be 1 and 2. And now you look further in the algorithm. There's going to be a then and there's going to be an else to this if statement. Here's the then, yes. Here's the else, no. And you follow the program down. And you keep following it and following it until you find the next if statement. You might follow it through a loop, but sooner or later you'll get to another if statement, and that will tell you what to do next. There'll be another question. Maybe 2 versus 3. Maybe if the answer was no, it would be 1 versus 3. The point is, this decision tree can be made out of any algorithm you come up with, and my argument is going to be based on this decision tree rather than any particular specifics of the algorithm you give me. You come up with an algorithm, I convert it to a decision tree, and I'm going to argue about this decision tree to show you that it's going to require a certain number of steps to sort a list. All right, well, we haven't quite finished the description of a decision tree. Every node is a comparison of 2 elements in the array. Every edge describes whether the answer is yes or no and goes to another comparison. What's at the bottom? What are the leaves of this tree? Dot, 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 dot. What do the leaves look like? Different orders, right? Let's say I'm trying to sort this. If I made it down to here, to this one little leaf, that means, let's say that the whole thing was sorted except 2 and 1 were out of place. So the leaves represent permutations of the original order of the numbers. This leaf might represent that the whole thing was sorted except I have to swap 1 and 2 to get it to be completely sorted. Except for 1 and 2 it was sorted. So I would write it like this. 2, 1, 3, 4, 5, etc. That's the permutation that you end up here. Maybe some other leaf might be the whole thing was in reverse order. So this reverses it. This represents what I do to the input to make it sorted. Depending on the sequence of comparisons you make, when you're all done, there will have been some permutation of the array made. And at the end, that's what the array looks like, and it represents what you did to it. Okay so far? That's a tricky part. So leaves represent permutations of the array, and internal nodes, as they're sometimes called, nodes that aren't leaves, represent questions, if statements. And every algorithm you come up with can be written as a decision tree. Okay. If your algorithm is going to work, then it needs to be able to sort any list of numbers I give it. That means it needs to be able to handle any permutation of the original list of numbers. It needs to have something that just switches 1 and 2. It needs to have something that reverses. It needs to have something that switches the 3rd with the 4th with the 5th and then cycles it around. It needs to be able to handle any permutation. It needs to have as many leaves in the bottom as there are permutations of n numbers. How many permutations are there of n numbers? There's n factorial. That means it needs to have, if it's going to work, n factorial leaves. If it's missing one of these leaves, then I will look at the leaf that's missing. Let's say it's this one that's missing. Let's say it's missing this one. It's missing the one that switches just 1 and 3. Then I will take a list and put it completely sorted, except I will have the 1st and 3rd out of order, and I will put it in your algorithm, and your algorithm will end up doing one of the other leaves on it, and it won't sort it right. If it's missing this way of switching the things around, then it won't sort this misordered list. It's got to have every one. Okay? That's the argument here. Which means, if you take your algorithm, turn it into a decision tree, your decision tree must have at least, and here's the lower bound, at least, you need at least n factorial leaves. There are at least n factorial leaves in any decision tree for any algorithm you come up with that's guaranteed to sort every permutation of the list. So what? So I got n factorial leaves. So what? How does this decision tree represent how much time your algorithm takes? If you looked at the decision tree, how would you decide the worst time of your algorithm? What would you do? The longest path from here to a leaf. That certainly represents the worst case. So all I have to do now is convince you that if you have any binary tree with at least n factorial leaves, that the smallest of the longest path you could possibly have has to be at least n log n. If I can convince you of that, then I'm all done. Then I'm going to show you that no matter what you try to do, if you have n factorial leaves, your longest path is going to have to be at least n log n long. So I have to show you, now we're back into math land, if we weren't there for the last 10 minutes. I'm going to show you that in a tree with n factorial leaves, the height is at least as big. The height of the tree means the longest path from the top to the bottom. The height is at least as big as n log n, some constant of n log n. But what's the best you could hope for a short height? You want the tree to be fat and bushy, or you want the tree to be wiry and scrawny and thin? What's the best you can hope for? Fat and bushy is the best you can hope for, right? Spread me out as much as possible, and I'll keep myself nice and squat and stable. Okay, and my doctor will tell me to lose weight, but at least I'll be close to the ground. Good. Thank you. If you have a bunch of leaves on the bottom of a tree, what's the height of that tree if you make it completely balanced as possible? Log of the number of leaves. So the tree here, if we make it as bushy as possible, which is the best we can hope for, that's going to make the height as small as possible. The best we can hope for is bigger than or equal to the log of n factorial. What's the log of n factorial? Do you remember we spent painful days explaining that the log of n factorial was both larger than n log n times a constant and smaller than n log n times a constant? The log of n factorial, I'll remind you briefly of this, is the same as the log of n plus the log of n minus 1 plus the log of n minus 2, right? Because I spread the log over the multiplication and I add the pieces up. So this is going to be smaller than n log n. Okay, because I have n pieces, each of which is log n or smaller. And it's going to be bigger than, and this is a much harder argument. I'm going to put a big recitation on this. It's bigger than, who remembers, n over 2 log n over 2. Okay, we did this in discrete math. We proved that log n factorial was less than or equal to n log n, bigger than or equal to n over 2 log n over 2. The key thing is that log n factorial is big theta n log n, which means the best you can hope for in this tree is a height of n log n, which means every algorithm you ever come up with can be converted to a decision tree with at least n factorial leaves if it's going to do sorting, and the height or the time that that's going to take in the worst case is going to be n log n. And it's all based on the math that shows that log n factorial is n log n. That's the lower bound argument for sorting.
What kind of assumptions does this make about the way we do math, or the sort of, I mean, this assumes you can only make one comparison at a time, or?
Right. It assumes that you can take any algorithm and divide it into steps where each step can be, it assumes that you're measuring comparisons.
And linearly done comparisons. I mean, as opposed to something like you're putting this in DNA and throwing out biological argument.
Right. It assumes that every comparison takes a discrete step. Right. Right. Absolutely. You're going to see the sorts we're about to talk about don't use comparisons at all explicitly. And because of that, they cannot be thrown into decision trees. Nevertheless, they don't end up beating n log n, but they would not fall into this category. So this lower bound only shows that it's n log n for sorts that use comparisons as their major tool. Okay, questions about it? Okie dokie? Donna, okay? Yeah? All right. Todd?
A little question.
I knew you had a question.
About uniqueness. What if we know we're sorting the words in a book, and the English language distribution is there's lots of duplicates? we've got unique permutations on the bottom. If we didn't require a stable sort, could we get better than n log n because we have fewer leaves than n factorial?
Yes, you could.
There's a little answer to a little question.
Yes. Yes. If there's duplicates, yes, you could. And that's an excellent question. It's a good question. And it's similar to how we're going to leverage some information for Radix Sort and Bucket Sort. Anytime, but you're assuming something about the input when you're trying to save there, and you need to, but sure, the answer is yes, you can do it. Well, it is possible that your program, if it goes through this sequence, sorts it this way, and if it goes through this other sequence, happens to sort it the same way. Kind of be a little bit inefficient, right. But yeah, it's a little bit of a mathematical thing. Any normal algorithm would have exactly n factorial leaves at the bottom. Although you could write one with more, and essentially, basically those two paths through your algorithm would do equivalent things.
Right.
God knows I've seen programs that do that, so it isn't so unusual. But yeah, I mean, good point. Yeah. Other questions? Okay, shifting gears. You're sitting at your desk. And instead of teaching at ADU, you're teaching at a place where the class has 632 people in it, and it's a big, big lecture hall. And you don't ever get to answer any questions, but you get to spend a lot of time grading the exam because the school's policy is the TAs are not allowed to grade exams. They can only do the other stuff for you. So you're sitting there with 632 exams, and you spent all weekend grading the 632 exams, and they're sitting there in a big pile on your desk, and you have to sort them by grade. All right, so what do? You don't do insertion sort because there's just way too much time. You can't imagine running through 632 and trying to find the right spot. I mean, it's just out of control.
Are we sorting by grade or by name?
By grade. By grade, yeah. Well, the thing about sorting by grade that makes this easy is that there's only 100 grades, right? Assuming you were smart enough to make the test just up to 100 instead of 550 or some other ridiculous number. If the test only goes up to 100, all you got to do is find a big room like this and set 100 empty spaces in front of you and walk around with the test one by one. And this person got a 75, so it goes in the 75 pile. This person got an 82, it goes in the 82 pile. And you go around distributing the grades one at a time into their appropriate pile. And when you're all done, you pick up the zeros first, and then you pick up the ones and the twos and the threes, and you move all the way up until you pick up the hundreds, and then you have them in order from 0 through 100. Everybody get that idea? It's much easier with a pop quiz. It only goes up to 10. Right? Then if you have 632 grades and they only go up to 10, you'd have to be a lunatic not to sort it this way. I think it's the only way anyone would ever think of is just make 10 spots on your desk and put them out. Boom, 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 boom. All right. We have to do this with a data structure and with a program. But this method is called counting sort, or what the book calls counting sort. And it's at the basis of bucket sort and radix sort. And it's at the basis of trying to have your sorts work in linear time. And as you can tell, it does not compare any of the grades one to another. Right? It just distributes them out into their appropriate slots. So the first question is, how do we do this with a data structure in a computer program? And then the next question is, how fast does this take? So in a computer program, here's what we do. Let's say that it's the grades go from 0 to 10. So we'd have an array that has indices 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll call it grades. And here are our grades. Etc. Hundreds of them. So here's what you do. You set up your array, and you put zeros in all these spots, because you haven't looked at any tests yet. So there's nothing in your array. And now you go through and you see, I got an 8. So if you go see an 8, you use that as your index, and you go to grades brackets 8, and you increment this value by 1. I'll do that by putting a slash here. 7 gets incremented by 1. 6 gets incremented twice. 5, 4, 9, 9, 9, 10, 10, 1. And you keep doing this and doing this until you're all done. When you're all done, you have an array with numbers in it. The number in index 9 represents how many scores got a 9. The number in index 10 represents how many scores got a perfect score of 10. And if you want to print these values out in sorted order, you would go through this array from 0 to 10, and for each slot, you would print the index as many times as the value in that index equals. So here you would print 0 0 times. You would print 1 once. You would print 2 and 3 0 times. You would print 4 twice. You print 5 once, 6 twice, 7 once, 8 once, 9 3 times, and 10 twice. And that would sort the list. You could even copy those into an array at the end, and you'd have your sorted numbers in an array. All right, so that's how you'd implement it. The code is in the notes. You can look at it. It's a loop or so long. And the question is, how long does it take? Well, what do you think? How many steps does it take? We have our normal way of measuring a sort is by the size of the number of grades, by the number of grades, n. So relative to n, what are we doing? We go through each grade exactly one time. We increment a particular index. That takes another step. So far, it's just proportional to the number of grades we have. What do we do at the end? At the end, well, at the beginning, we have to initialize these values, but that only takes 10 steps. We initialize them to 0. At the end, we have to go through and run through all these values again, printing out each index depending on how many times the value is stored in there. How long does that take? It takes n. Only n? N plus possibly, because we have to look at the zeros too. So n plus 10 in the worst case. The key thing about this is that it really does take linear time, but if you keep in mind that we have this restriction that all the numbers are between 0 and 10, that's what makes it linear time. How fast would it take if I didn't have a restriction on the size of my input? And I called the highest number that actually shows up m. So I have a variable for it instead of 10. Then the complexity ends up being big theta of n plus m. The plus m comes from the beginning when you initialize it, and comes from the end, because let's just say, here's a good way to get the sense of the plus m. Let's say all the numbers ended up being 0. I got a class full of zeros, 792 zeros. Okay, so I go to 0, I print 0 out 792 times, okay, and now I have to go to the rest of these to see that they're all 0. So that's an extra m minus 1, but order m. So together it takes n plus m, where n is the number of different elements, and m is the largest of what those elements could possibly be. That's what counting sort really takes. If m is a constant, then this is big theta n. It's linear time.
More precisely, shouldn't m be the difference between the largest and smallest? Because we might not always be dealing with something that starts at 0.
Yes.
I mean,
m is the number of... It's the range. That's right. M is the range. Right. Now what could the range be? Well, it's unlimited. I mean, it could be 2 to the n. It could be exponential in the number of numbers we have. So this is a ludicrous algorithm unless you know that m is a very small number. Certainly constant with respect to your n. It certainly can't grow as your n grows. And generally speaking, the more numbers you get in a normal situation, the bigger your biggest one might be. Normally the biggest one does grow. Normally the range does grow with more numbers. Normally. But if it doesn't, then you're lucky. Then you can use counting sort. Okay, questions so far? This is the pure version of counting sort. But what we'd like to do is leverage this and use it even in the cases where we don't have a fixed value for the range. Even in the cases where we can't guarantee that. Because it's such a nice idea, we got to be able to pull something out of here. And radix sort and bucket sort are two different ways of leveraging this idea. Yeah, John?
Presumably another restriction is that this really only works for like integers and strings where the values are in a very discrete, it wouldn't work for floating points or anything like that.
Right, right. And you'll see the first way we're going to leverage this is a way of trying to take situations like that and convert it back to discrete values. Right, good point. That's a very good question. I like that. I'm borrowing that. Thank you, Gil. All right. So, any other questions about counting sort? We're shifting over. Bucket sort. You should know that in some old textbooks, most actually, counting sort is indistinguishable from bucket sort. You'll sometimes see bucket sort and they'll describe this sort. So be aware that this textbook decided to make the distinction clear, and from now on probably people will use this notation, that counting sort is this and bucket sort is a special version of it that I'm going to explain right now. So in bucket sort, it turns out we have no maximum at all. The range is virtually indefinite. Let's say, in this particular example, you sort a bunch of numbers, and the biggest one ends up being 99,999, and the smallest one ends up being 0. It's a big range. You can always figure out the range, right? You could always find the max and min and figure out the range for any particular thing you're sorting. That only takes linear time to find your range. So you can always find your range. And we found it in this example, and it's very big. The number of numbers we're sorting is only on the order of, say, 100. So if we're sorting 100 numbers, and each one can be between 0 and 100,000, then we're not going to use counting sort, because if we do, it's going to take time proportional to 100 plus 100,000. And that's horrible. We could just do n log n on 100 using heap sort and do better than that. So we can't use counting sort to sort 100 numbers in the range 0 to 99,999. But we can use something really similar to counting sort. We can leverage counting sort over to bucket sort, but we have to make one assumption. We're going to make the assumption that the 100 numbers we have are uniformly distributed in this range. That they're not bunched together anywhere, but they're spread out in some kind of a normal distribution. That's the assumption implicit in bucket sort. Without that assumption, the analysis will not give you anything good. With that assumption, the analysis will run in linear time. So we're going to assume that the 100 numbers, are spread out evenly. And here's what we're going to do. Well, you might even be able to think of it yourself. If these numbers are spread out evenly between 0 and 100,000, then how can we use counting sort even though the number here is really big? What could we do? Chop it into pieces. Each piece, how many pieces? Well, we got 100 numbers. Let's have 100 pieces.
Do we have to know the limits of the sort of the range?
I think you do, yes. At least the version that I'm describing, you do. So you're going to chop this into little pieces. Each piece is going to be 1/100th the size here. So it's 100th of 100,000 is about 1,000 big. So 0 to 1,000 goes here. 1,001 to 2,000 goes here. 2,001 to 3,000 goes here. And we're going to have an array like we did last time called grades. And grades is going to go from 0, 1, all the way up to 99. 0 represents any score that is between 0 and 1,000. Grades of 1 represents any score that's going to be between 1,000 and 2,000. Grades of 2 represents scores between 2,000 and 3,000. Okay so far? How do I go ahead and use this? It's a little trickier than counting sort. I look at a score. I've got a bunch of scores. 35,689, 12,582, 98,563, 3,126. I look at 35,689. What do? I go to slot 35, and I increment it by, this is fine. When I'm all done, say I have 5 numbers that are between 35,000 and 36,000. What am I going to do at the end? I'm going to print out 35 that many times. What happened to 35,689 and 35,123? They're gone. I lost them. Well, that sucks. We can't do that. Can't lose the numbers. So what do I really put in here in 35? I got to actually remember the numbers that I put in. I can't just increment and count.
Just put the last 3 digits.
I could do that. I certainly could. I certainly could. But I need to remember something about this number. And I can't just say, I saw another one of them. So somehow I'm going to have to remember 35,689. And if there's another one afterwards, like over here, 35,123, then that'll come afterwards, 35,123. And at the end, when I'm all done, I don't just look at a single number that's in this slot and print out 35 that many times. Instead, I go to this index, and I go to this link, and I run down the arrows, and I print out these numbers.
You should probably sort them first.
They're not sorted.
Right, they're not sorted. But if they were, I'd be okay, right?
Yes.
All right, let me back up. I've done the same trick I did before. Let's analyze. We are going to have to sort those, but let's analyze. I look through each of these numbers exactly once. Each time I look through them, I go to the appropriate index in constant time, and I do a constant time operation. I add a data value to a linked list. That's a structure where I can just tack it on the end and dynamically add a new value as I go. Data value, and then an address that points to where the next one is. Mark's going to do a very, very good review and detailed intro to those of you who don't know linked lists at all about how to do this on Monday. But it's a structure that runs dynamically, and you can add things to it in constant time. Still order n so far. What happens at the end? I go through each of these indices. If there's things in it, if it doesn't point to nil, if it's empty, I do nothing. If it's empty, I do nothing. But if there's something in it, like here, I run through the list, printing it out. This way, the same as before, I'm going to hit every number that was in my list exactly one more time, and all the empty slots I might hit once that have nils. So it's the number of numbers in the list plus the number of intervals that you created. Same kind of complexity as before, but you got to choose the number of intervals. And I picked it exactly equal to what? To the number of numbers I had. So in this case, it's going to work in this time, because my m is equal to n, because I picked a number of intervals equal to the size of the numbers I had. So this is a way to leverage counting sort. Do you see how it's not the same, it's more complex, but it's the same idea at the foundation? Questions about this?
Well, the theta n plus n has not sorted the...
Right, we haven't done that yet. Right, so now we're at the fussy part. Legitimately important fussy part. Look, if I just put these in randomly, they're not necessarily sorted, right? So the truth is that when you're done putting everything in, before you go through and print them all out, you have to go one spot at a time to these little linked lists, copy them over to a little array, sort them around, and put them back in the linked lists. Let's consider the worst case, where they're not uniformly distributed. In fact, all the numbers start with 35,000. I lied. I said bucket sort is great here because they're uniformly distributed, and instead I came up with 100 numbers, and they all start with 35,000. And when I went through this algorithm, everything here is empty except for the slot that starts with 35, and that's got all the 100 numbers in it. So how many steps did it take so far? It took me 100 steps to fill this with 100 numbers. Now I have to take this linked list, copy it over, sort it. How long does that take? N log n. Copy it back. That takes another n. And then print it out. That takes another n plus n. So everything takes n, 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 except for that one little step where I have to copy all these out and sort them n log n. And why the heck didn't I just do that to begin with, since they're all starting with 35,000? So the answer is that you are dead, and you're just gone if they all end up in one spot. Yeah, you have a point,
We
Doug?
could recursively call bucket sort on this, knowing that it's now spread in only over 1,000 numbers.
Radix sort is a little like that. So hold off a second. Okay? Good. The point is, if our assumption that these numbers were uniformly distributed among the different intervals was true, then the probabilistic analysis shows that this doesn't happen. Or if it does happen, it happens with a probability so infinitesimal that when you average it over all the probabilities of where the numbers might end up, it doesn't have any bad effect. So if you do the hairy analysis, averaging over the probability distribution of where these numbers end up, generally speaking, let's consider the best case. The best case is that you get 1 in every interval. Then there's no sorting to be done. But generally speaking, what you tend to do is get a constant number in every interval. So the sorting step is basically a constant number times the different number of intervals you have. For example, if you got at most 3 in any interval, it only takes 7 or 8 steps to sort 3 numbers, so it's 7 or 8 times n. So if you know it's a uniform distribution, you can really leverage this trick. But if you don't, it's bad. Yeah.
But uniform can be relative because you could set. There's no reason why you have to set the intervals to be precisely equal.
You could perhaps pick your intervals to make the distribution be, quote, uniform.
Yeah. Normal curves, you would have wide buckets on either end and narrow buckets.
If you had information about the distribution of your numbers, you could possibly pick the intervals to make the distribution, quote, normal or uniform. Yes, you could. You could.
There's another concern too. When you're finished with the sort, you want to date in some nice structure to look at it. And that bucket thing looks like a mess.
No, but you would copy them out just like before, Neil.
Then you copy it to another array.
Copy to another array, and it would be right there. Right, and that only takes another 2n steps. Yeah, so it doesn't hurt to do that. That's bucket sort. Yes?
Are there any algorithms that would analyze your data set before you attempt to sort through it? Tell you what algorithm would be good to call?
I don't think there's any algorithms to do that, but I bet you there's probably programs that do that. And I'd say there's no algorithm because I don't think there's any systematic way. I think it's a very ad hoc engineering kind of a problem to deal with. But I bet you there's back in the 80s, they would have called it an expert system to decide on the best sort for your particular data. And actually, Sam Klein Jr. wanted to run a recitation on, here's a real life problem, what sort do you want to use? So he would be the algorithm. Or the recitation would be the algorithm. It's a good thing to think about, but it's a hard problem because there's so many different features that you'd want to work with, and they all interact in different ways. So I don't think there's any algorithm to do it, but it's certainly a good problem to think about. Other questions? EJ, okay?
Yep.
Thumbs up, all right. Good. Good, good, good. Okay, last topic for today. Is somebody booing?
He's a Radix Sort heckler.
He's a Radix Sort heckler. Okay.
Okay, I'm a Radix Sort advocate.
A Radix Sort advocate. Okay. 2 men enter, 1 man leaves. Into the Radix Sort box.
It's all about the Thunderdome with you, isn't it?
Yeah. I like that movie. I like the way the mob kind of just loses it and goes, 2 men enter, 1 man leaves. It was like this complete... We're not even listening to the fact that what we're really saying is that we want to murder a person in the sporting event that's about to occur. Or maybe they were thinking about it. I got to watch more Roman gladiator movies. When I was in Israel, there was this old, what do they call them, hippodrome things?
That's horses. Horses is
That's where you...
Oh, so this was a hippodrome. Well, I told my kids that they killed people there, but it was a horror. Anyway, so the thing about this town that it was in, you know, they have so many ruins in this town, a town called Beit Shan, that some of them are actual national parks, but there's not enough money to make them all national parks. So this particular one is just right in the middle of town. You drive your car on this little dirt road, you park it, and there's a bunch of kids cooking potatoes, you know, in a little fire in the middle of this thing. No sign, no guide, some rusty old plaque that explains vaguely what it is if you can clean it up and barely read it. So I forgot what I was going to say. Jesus. Let's talk about Radix Sort. Anyway. I'm getting really old. All right, stop laughing now. What are you laughing about? Okay, here's a bunch of numbers. Let's sort them. Here's the idea of Radix Sort. Radix Sort actually is interesting because historically it connects to some cool inventions. I think in the United States in 1880 it took them 10 years virtually to finish the census, which is mandatory by the Constitution to count everybody in the country. So 1880 the trade-off between the technology of how they could do the counting and how many people were in the country made it just about got it done when they had to do it again. So they had to invent some kind of a mechanical way to do it. And the mechanical way that they did it was with some sort of punch card mechanism. And it turned out that the way that you sort punch cards in this machine is exactly the way that Radix Sort works. And in the 1960s, when IBM started making punch card machines as the way you input programs, which I used even in grad school, and these card readers would read your programs, and if you ever wanted to sort your cards in any kind of a meaningful way, it would sort it using a method exactly like Radix Sort. And it's a really cool trick. And you might even know this trick. So here's how it works. And it's a little like what Doug mentioned before about kind of recursively doing a bucket sort. Here's the idea of Radix Sort. Let's assume for now that all our numbers have exactly 3 digits. Okay? And we'll talk about that assumption later. But let's assume that they have 3 digits, and we want to sort these numbers. So the idea of Radix Sort is to use the counting sort trick on the least significant digit of these numbers. In other words, the 2 is going to come up, and then the 4s, and then the 6s, and then the 8, and then the 9. Let's actually do it. What's the order that my new set of numbers ends up being in?
672.
Thank you.
234. 534.
The 234 better have come before the 534. Good. Oh, good. Chris knows how to do it, right? You look through these things, and you're just going to do a counting sort. If you see something that ends in a 9, you put it in the slot for 9. If you see something that ends in 4, you put it in the slot for 4. And just like the bucket sort, if there's 2 things that end in 4, you're not just going to increment the 4 by 2, because then you'd only have 2 4s. You have to actually keep a linked list and remember 234 and 534. So there they are, 234 and 534. And what's the next one? 356, 256, 596, 348, 179. All right.
Why do you have to keep a linked list?
Because we have 0 through 9. And what we're going to do is run through these numbers one at a time. And if we get something that ends in a 9, we're going to put it here. Something that ends in a 6, we're going to put it here. Something else that ends in a 6, it goes here. And then later we're going to go through the whole array, copying them out back into an array that looks just like this.
Oh, I see what you're saying. You could do the same, well, or if you're keeping it in linked list format, you could just attach the heads to the tails. But if you're doing an array, you can do a single pass and just count and do a hash like you did before, and then stream everything into an array and just count. You already know, like you can do the, oh, you'd have to do some addition.
Yeah, but this way doesn't take more than, how many steps does this take? We have to go through all the input once, And then when we're done, we go through it once again, and we copy it back into an array. So n plus n. So it's order n to get this done. It's order n because there's only 10 steps, right? Otherwise, every step would be ordered. It's really order n plus 10, right? But it's fixed at 10 because this is base 10. So we know that each value in this column has a range of 10. So that's what we're leveraging here. We're assuming that there's a fixed number of columns, and each column has a specific max. So in one step that took order n, from here to here, order n, we got to this list. We're going to do the same thing again, and we're going to use the same array, because now it's ready to be used again. Notice this is not in place. We have one array that holds this, and one array that holds our values with our linked list. So this is not an in-place sort. We need the extra space. We're going to do it again, and now we're going to sort on the second column. It's really, really, really important that when you're sorting on the next column, that you have a sort that's stable. In other words, oh great, I don't have a good, you'll see in a minute why it's so important. Let's do it. What happens when I go sort on the second column now? 2, 3, 4, 5, 3, 4, 3, 4, 8, 3, 5, 6, 2, 5, 6, 6, 7, 2. Did I get them all? 1, 2, 3, 4, 5, 6, 7, 8. Good. Now if you look at the list, it's completely sorted from its middle column to the end. We're going to do it one more time and get the whole thing sorted. Running it back through our auxiliary little linked list bucket kind of a thing, and then seeing what our final list ends up being. So now the 2, 3, 4, sorry, the 179 comes first, but this is really important. What's going to come first, the 2, 3, 4 or the 2, 5, 6? The 2, 3, 4 comes first. What if the sort we used to do this was not in place? Sorry, was not stable. In other words, these two that were equal could flip.
You have to go back and sort it again.
We'd be dead, right? It would make all the work we did so far worthless. What we've been doing so far is we've been getting all these things in order so that at the end, the stuff that's equal, to distinguish between the equal ones, they're already in perfect order. The 2's that appear here are in the right order. The 2 that appears here is ahead of the 2 that appears here. 3, 4 is ahead of 5, 6. So you want to make sure that whatever sort you use to get to the next stage from stage to stage is a stable sort. And it turns out that bucket sort or counting sort is a stable sort. So we're okay. But who asked me? Donna asked me, when do you ever really need a stable sort? Well, here it is. You can't, if you use an unstable sort to do your successive stages in Radix Sort, then it messes you up big time. Okay. What do we got? So 2, 3, 4, 2, 5, 6, and now we're up to the 3's. 3, 4, 8, 3, 5, 6, 5, 9, 6. Oh, I missed it. 5, 3, 4, 5, 9, 6, and 6, 7, 2. And that list is sorted. You should note that if we did it in the other direction from the most significant, which is what a lot of people try to do when they first think of Radix Sort, you actually get a completely wrong sorted list. It doesn't work out well. You can try to salvage this. If you think about what happens, you end up actually taking a lot of extra time to do it from left to right and make it work. You can make it work going from left to right, but you don't get anywhere near the efficiency you get going from right to left. Going from right to left, we use this auxiliary counting storage. We copy it right back into the array, and we repeat. And every step takes order n. So we get n here, and n here. How many steps altogether? 3n, or how many digits we have. In this case, it's 3, but Doug's right. In general, if you have n numbers in your list, The biggest number is typically, if you're going to have different numbers, the biggest number might be as big as 2 to the n or bigger. So if the size or the number of columns here gets to be 2 to the n relative to the number of numbers you have, well, you've just got an algorithm that runs like this. That's terrible. So radix sort is only worthwhile when the number of digits in your number is constant relative to the number of numbers you have. The similar kind of constraint to counting sort is similar kind of constraint to bucket sort. Basically, a restriction on the size of the number with respect to the number of numbers that you have. Okay, questions about this? But if you do have to sort things that are bigger than that, then you have to use fancier data structures. You can't actually sort them just stored in a number. Like how does Lisp or Scheme do all that? How does it do comparisons between numbers, that are 100 things wide? It just stores them in these long linked lists, and each comparison actually takes time proportional to the size of the number. So you're right, any real numbers, right, but if you really want to do infinite precision arithmetic, it really does take a long time.
Yeah.
So it's,
You don't do that if you're a mathematician.
yeah, I guess you don't really need to compare numbers that are, well, unless you're encrypting things, with, right, 128 bits or something, but there's no real comparisons going on there. Other questions about this stuff?
Does this work significantly different if we're dealing with bits, with the numbers in bits?
No. It's very much the same, except that here instead of 10, we'll only have 2 categories. And it's a little easier to see that each successive stage is linear time, because doing a counting sort on just zeros and ones is just like that Same game, where the ones are basically dropping to the bottom and the zeros are coming up to the top.
My concern would be the speed would not be as good because we're going to have so many columns of bits relative to it.
Well,
if it's base 10.
That's true, but actually the relationship between the number of bits in a base 10 number and a base 2 number is a constant relationship. Log 2n and log 10n relate by log base 2 of 10. So it's times 3, so it's worth a constant. So yeah, again, it's an engineering issue, but not a theoretical issue at least. Other questions about radix sort? Yeah, Neil.
What's the shell sort? This sort that we're
It's in a category all by itself, and it's very, very interesting. And I left it out of the course because it would take much of a lecture to describe it. The interesting thing about shell sort is that the complexity, rather than being n log n or n squared, is basically n to the 1 point something, where that something is very small. And shell sort, more than any other sort, has all sorts of really cool experiments with it, where it tends to virtually seem to run very close to linear time, but theoretically you can prove n to the 1.5 and maybe a little bit less than that. And it has nothing to do with shells. It's named after a guy named Shell, I think. So don't get any intuition in your head about shells. It's not that. We can make that a topic of an advanced recitation. That would be a nice idea. No, it's iterative with different sizes to the phases of the iteration. That's the basic idea. It's not going to explain much in 2 seconds, but it's a neat thing to look at. Okay, other questions? We're up to searching. We're up to binary search trees. We're going to talk about red-black trees, a new data structure you've never ever seen before, and this will take a couple of days. We'll talk about finding the median. Obviously, you can find the median of a bunch of elements by sorting them, right? And then just picking the middle one. But you got to do better than that. So we're going to look for a linear method of finding the median, of finding the middle, and that'll be our segue from sorting to searching.
Before we move on from the sorting, I'm just curious, how often do programmers really deal with sorting? I mean, we've spent quite a bit of time talking about it. It seems like it's a big topic, but is that...
Oh, it was a big topic maybe 30 years ago. I mean, no, if you want to do a sort, what? You go on Unix, there's a little command called sort, right? And it works. I'm serious. I mean, most of the algorithms that you're going to use, look, I'm going to back up even further. Most software engineers don't do anything except write stuff that runs in a loop and processes data coming in and make sure it looks okay coming out. It's just a lot of busy stuff relative to algorithms. That's most programs. When algorithms do come up, they tend to usually be things that people have discovered. And they're there in packages, and you use them. Then there are maybe the 5% of people that really are working on projects that require somebody to come up with really a new idea, a variation of something somebody's worked on, a new angle on, say, string matching, because their particular product has strings that are of particular distribution, and the normal string matching algorithms run a little too slow, and they'd like to make it a little faster. So they got to go study it and figure it out. So it does come up, but it probably comes up in a minority. In 5 to 10%, I think of serious programming jobs. People writing compilers, people building serious complex systems, not people who are building websites. The average person who's building a website is not going to ever have to deal with a hard algorithm. I'm probably wrong about that. But the people that I know that are primarily making pretty pictures and just setting links up in an organized fashion, that takes an aesthetic point of view, and it takes an organization in software engineering, but it doesn't take an algorithm. People over at Akamai that figure out how to make web farms so that nobody gets a delay when they're looking for something, there is an algorithm behind that, which is the key to the whole company. And the people who created that company are all theoretical computer scientists. They're all people who I've seen give talks at conferences about algorithms. That's their main work. Who's in that company? Charles Liserson and Tom Layton. These are all mathematician types. And their company's probably one of the most practical companies. So I don't want to make it seem like, it isn't there. It is there, but not for the average guy programming, probably. Yeah.
What kind of graphics or imaging work is going to be algorithm heavy?
That's very math heavy, imaging and graphic stuff. But a lot of the math is also well known, and academic people work on that all the time, and then they present Silicon Graphics will give you something built in that will do the rendering for you. But the people who built the rendering algorithm need to know about the math.
Yeah, that's what, if you're not working at SGI.
Right.
If you're working at SGI, you are doing it.
If you're working at SGI, you're doing that stuff. If you're going to use their stuff, you won't. You'll just use it, right?
Well,
Yeah, yeah. There's plenty of jobs that use this stuff intensely. There's a lot more that don't. I mean, look, how many software people are there? I mean, how many people program for a living? 1 million? I don't know. Does anybody know how many people program for a living? How many programmers are?
It's got to be about 1 million.
I bet so.
If you add up the number of kind of certified Java programmers, certified ASP
Yeah, and just
programmers,
it must be.
I mean, Java alone is like 500,000.
So how many of these million actually do algorithms in their day-to-day work? No, I'd say a few thousand is legitimate. I mean, I occasionally get somebody sending me an email who's a software engineer for a living and says, hey, do you know how to do this? And I'll refer them to some papers, and then that's always a gratifying moment, because at least I get to see somehow the interface between people who just want to make something work and get paid to do it, and other people who just want to do stuff that seems cool and get publications. And every once in a while, there's a nice little interface, and they share stuff. I mean, you hope to God it is, right? But there really is, especially in computer science. Okay, let's quit.